not really way fast.
I know you definitely know how to sing.
I know. No, I got something to say my brother.
I know.
And I was
Sing. He's like really calm. He just randomly.
my dad.
Alright. So I will try to have your lessons up while you're taking the test, so you can have those printed off ready to go. So choose to do that. All right. At the end of this lesson, you'll be able to define acceleration mathematically and conceptually. Yeah, they switched it over to just regular gasoline. Yep. Yeah, it's crazy. Yep. Know when an object is undergoing acceleration. Make a distinction between velocity and acceleration, and make an acceleration versus time graph from a velocity versus time graph. That's what we got on the docket today. So, acceleration, the definition, textbook definition is the rate at which velocity changes. The rate at which velocity changes. Okay? A little bit more down to earth explanation of that is how quickly you are changing your speed. How quickly you are changing your speed. Okay. The variable for acceleration is a lowercase a, and the equation is delta v over delta t. So change the rate at which velocity is changing. You could expand that to final velocity minus initial velocity over final clock reading minus initial clock reading. The units for acceleration, we can figure that out from the equation. What is the unit of velocity? What do we measure velocity in? Perfect. Meters per second. And what is the unit for time? Seconds. Meters per second is the unit of acceleration. Okay? Now, mathematically, we can simplify that to meters per second squared. But if you were to follow up with a question like, what's a squared second? I don't know what to tell you. I can tell you what a square meter is, but a second that's squared, I'm like, So this is a convenient way to write this, but to explain it, this is the way. It's meters per second. So, for example, if I had an acceleration of 5 meters per second, what that means is my velocity is changing 5 meters per second every second. So my speedometer would look like 0, 5 meters a second, 10 meters a second, 15 meters a second, 20 meters a second, 25 meters a second. Every second that goes by, I'm changing my velocity by 5 meters per second. Okay? And we simplify that to meters per second squared. A more convenient unit for us driving would be miles per hour per second. So if you had an acceleration of 5 miles an hour per second, your speedometer will look like 5 miles an hour, 10 miles an hour, 20 miles an hour, 15 miles an hour, 20 miles an hour. Every second that goes by, you're changing your velocity by 5 miles an hour every second. All right with that? But we're in science class and we use metric system. Good? Okay. Take a shot at that. Have a conversation. Why do you think so? Everybody knows what cruise control is? Or it's the function, the feature that you can lock in your speed without pressing your foot on the gas pedal.
I was like, wait.
Yeah.
Correct answer is A. A? Why is it A? Right, because the velocity is not changing. Okay? In my experience, there's a lot of confusion between velocity and acceleration. They are completely different things, and my objective is today is to make a distinction between those in your brain. Okay? So you can be moving, you can have a velocity and not have acceleration. That is a thing. Okay? Because your velocity is not changing. Next. Neighbor? Why do you think so? How?
Yeah, because it's like, but it's like, if it, yeah, because it's like, I had to read this three times, I was like, yeah, it doesn't change. Yeah, so I felt like just.
Oh.
Yeah, because I watched it. Yeah. Like it's not actually screwed on or anything, it's just like, yeah. One I'm not moving. He's like, I'm like, I like, at the football tournament, last week there was like a dumpster full of this. I was like, dang.
Correct answer is? Okay, everybody is good with A, right? Like that's, okay, like speeding up is acceleration. Okay? Slowing down, like, is velocity changing? Yes. Okay? I'm just gonna throw this out here. I hate the word decelerate. It leads people down errant, wrong thinking. Just throwing that out there. Okay? Replace that with slowing down. Okay? Velocity communicates two things. It communicates speed and direction. If you keep the same speed but change the direction, is that a change in velocity? Yes. So all three of these, if you change any of them, constitutes considered. In physics, we consider that acceleration. Okay, so I'm broadening your definition of acceleration. Okay, with that, in physics, if you change anything with velocity, that means you have acceleration. Experiencing acceleration. Good with that? Talk to you. Tell them why.
I'm writing a lot. They're really growing on.
Correct answer is? Correct answer is the bike. Okay? It experienced a greater change in velocity during that time than the car did. So acceleration is not about how fast you're going. It's about how quickly you're changing your velocity. You all right with that? Thumbs up when you have a guess. Tell your neighbor. Tell them how you got to that conclusion. Correct answer is? Correct answer is C. Okay. We've got a conceptual explanation and a mathematical explanation. You need to be familiar with both. Okay. Conceptually, you experience an acceleration of 2 meters per second, which means speedometer, her speedometer looks like this. 0, 2 meters a second, 4, 6, 8, 10, 12. Okay, every second that goes by, you change your velocity by 2 meters per second. Mathematically, you have this equation. Final velocity minus initial velocity, that's change in velocity over the time interval. 2 meters per second squared is equal to final velocity, what you're looking for, minus 0, because she started at rest, over 6 seconds. So you can find that by going 2 times 6 gets you 12. Good? Okay. You need to be familiar with being able to do it conceptually and mathematically. Okay. Sometimes, depending if you're a math kid or not, if you're a math kid, you start with the math and then use that to help direct your concepts. Sometimes you're conceptual and help use that to direct your math. So you need to have both tools in your toolbox. Okay. All right, everybody get out your speedometers. Okay. Show me speeding up with a constant acceleration. What does speeding up with a constant acceleration look like? Good with that? Show me speeding up with an increasing acceleration. What is speeding up with an increasing acceleration? Does that make sense? The rate at which you're speeding up is increasing. Think about this next one. Show me speeding up with a decreasing acceleration. Don't do it yet. I just want you to think about it. Speeding up with a decreasing acceleration. Show your neighbor. Okay. This one's always interesting. People are like, is that a thing? Okay. This question really gets at distinguishing between velocity and acceleration. Okay? Speeding up with a decrease in acceleration. You are speeding up the entire time. Your speedometer never does this. Okay? That's not speeding up. That's slowing down. Does that make sense? Speeding up with a decrease in acceleration looks like this. Okay? You are speeding up the entire time, just the rate at which you are speeding up is decreasing. Okay? Your speedometer is how quickly your speedometer moves. It's moving fast here and it's slowing down here, but you are this is actually how your cars speed up if you punched it. Okay, it's like as you get faster, it's harder to do that. Does that make sense? Okay, you're speeding up the decrease in acceleration. Good? Yeah. Have a conversation.
No, actually, it's. Because it's actually just like 9 seconds. It's so just less than 5 seconds. No, the difference between 0 and 9 and 1, you have 50% chance.
Correct answer is? Correct answer is B. Okay, at the end of that one Mississippi, when you hit the Ippy, you guys know what I'm talking about when I say one Mississippi? Like, okay. At the end of that last I, your speedometer started at 0, it's now at 5 meters a second. Okay with that? Okay. This next question is the same scenario, but it's asking a different question. Have a conversation. Why do you think so?
Per second, for every second. We wouldn't have said. The whole time. By the end of the time, you get to 5. Unless as soon as you put the velocity there, it's 5. Guys, I don't know. I think you're right though. No, I just don't think like that. Like, I know. That makes sense.
Correct answer is? Okay. Correct answer is C. In order to do 5 meters, what would have to be true about your speed? You'd have to be going 5 meters per second the entire 1 Mississippi. Does that make sense? Like your speedometer would have to be 5 meters per second the entire second. But you only reach there at the end of the Ippy. You all right with that? Okay. Later this week, I will give you an equation that we'll actually be able to calculate how much that's going to be. But for right now, does that make sense why you cannot reach 5 meters? Okay. All right. So, slope, rise over run, changing y over changing x. We've already had these conversations. But now let's apply this to a velocity versus time graph. Okay. What is on the y-axis on a velocity versus time graph? Velocity. So change in velocity. What's on our x-axis? Time. Change in time. Huh. What is this ratio of delta v over delta t equal? Craziness. Okay. So the slope of a velocity versus time graph tells us the value of acceleration. That phraseology kind of seems familiar, as it should be, because the relationship, this is the exact same relationship that we had with a position versus time graph and a velocity versus time graph. the slope of a position versus time graph tells us the value of velocity. The slope of a velocity versus time graph tells us the value of acceleration. It is the exact same relationship. It's just another step in that relationship. In calculus, we would call that is the second derivative. If that means nothing to you, fine, let that fly over. When you get there, you're like, that's what Smiley was talking about. And I'm so glad for physics. This relationship, you're going to use the exact same thought processes, the same thinking that you had when you were trying to look at position versus time graph to make a velocity versus time graph, using the same thought processes to make acceleration versus time graphs. Okay? Thumbs up when you have something. Converse. Tell them why.
We drive my car. Oh, we this morning? Yeah, I'm sure we're not gonna die in a car crash if I drive. No, you just need to go up with air and something. Yeah, yeah. Like, I can check my tire pressure. My dad is yeah, I don't even know, like, I'm so scared. I think even my oil changed for like a while. So I forgot I had to like actually do maintenance stuff.
Correct answer is? Correct answer is C. Okay, you need both. I'm going to give you both like a conceptual story and mathematically and graphically. How would you move to produce this velocity versus time graph? Like an emotion detector, what would you do to make that? You're moving at a constant velocity in the positive direction, so away from the motion detector. Good with that? Okay. So the fact that your velocity is constant means it's not changing, so you have zero acceleration. Okay, that would be the conceptual story. Mathematically, graphically, what is the slope of this line? Zero. The slope of this line is the value of acceleration. Good with that? Okay, you need to be able to do both conceptual and math graph type stuff. Okay? Tell your neighbor. Tell them why.
Oh, I just Because if it high velocity, low time, and then low velocity, high time, so it's like different slopes.
No razor, bro. Like no hair on top of your head.
So it's like 10 over 2 versus 5. And then it's like, if it's like 2, then mass 1,
That would be primary on
but like it's high.
right now. Like, I don't know.
I think it is. I feel like it is.
Correct answer is? Okay. To make this graph, you would have to move how? Okay. Are you moving in the positive or negative direction? Positive direction. Are you speeding up or slowing down? You're slowing down. And you're slowing down at a constant rate? Okay. So you're slowing down at a constant rate, it's going to give you a negative acceleration. Okay. The slope of this line is it positive or negative? The slope of this line is it positive or negative? It's a negative slope. Is it constant or is it changing? The slope. It's a constant slope. So you have a constant negative slope. You're going to have a constant negative value. Okay? Let me give you this insight. For this class, we are assuming that acceleration will be constant. So what that means on a graph is acceleration versus time graphs will always be horizontal lines. Positive, negative, or zero. That's really all I care about. Okay? So on a test or a worksheet or whatever, if I give you a choice of acceleration versus time graph that looks like this, you'd be like, oh, Mr. Smiley, you're trying to trick me. We don't do that in this class. Okay? This would require calculus. Okay? We're not going to do in this class. Good with that? Okay? So, acceleration versus time graphs, horizontal lines. I'm going to skip this one. Correct answer, you can circle it on your notes, is B. Not that important a question. Try this one. Tell your neighbor. Tell them how you know.
Well, I got it.
Okay, correct answer is A. You slow down quickly, small amount of time, steep slope. Here's 8 seconds. Okay, same scenario, different question. Acceleration versus time graph. Is everybody good with C? Has a really steep, therefore like a large negative value. Here, not so much positive. Good? Last question. Correct answer is C. They have the same slope. The rate of change is identical. Okay, good with that? You have a pre-quiz due tomorrow. We-